Good morning, physics students, and welcome to another episode of Physics. It's Mr. Finn. Welcome to a Friday, May 1st. I'm hoping you guys are having a great time today. We got to get ready for our big Google form today, so you might need a little bit more review. I'm going to go a little shorter on the recording today. Just give you a couple things to review for the big Google form today on combination circuits and to wrap up series and parallel circuits in general. Now, I did get in a question through email that I wanted to address today, so I want to do that as well. That's on the back half of chapter 34 about the costs of running a light bulb continuously. So I'm going to go through that, but before I do, let's get a couple of general trends with series and parallel. Okay, guys, for the series circuits, we know that we can add resistors together in series. In a series portion, so if we break our circuit down and it becomes all series, we can simply add those resistors up by normal addition. After that point, we would use whatever voltage we have, and we would use Ohm's law with the total voltage divided by that total resistance to find ourselves a value for current. Current can then be applied to each individual resistor to find applied voltages, otherwise known as voltage drops. You can add those voltage drops up and get the total voltage. So in series, you can add resistors together to find total resistance, and you can also add the voltage drops together to become total voltage. How does that differ from parallel? Remember, if we have a parallel shell, we apply Ohm's law individually right out of the gate to each branch to find those branch currents. Because in parallel, the branch currents add together to give you a total current. But resistors do not add together in parallel. Remember, we had those two special formulas for finding the equivalent resistance. 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3, or however many R's you have. The shortcut, if you have just two non-equal resistors, is R1 times R2 over R1 plus R2. So remember, we cannot add resistors as the overall paths goes up in parallel. If you add bulbs in parallel, the overall resistance goes down because the current goes up. And remember, we cannot add voltage drops in parallel either, because as long as there are branches, each of those branches would get the same voltage. And if that's the only thing you have in the circuit is those branches, then each of those branches would be the same as the total voltage. All right, guys, make sure you get a chance to go over the examples in the book and the examples that we've done as part of our study all of this week. We've sure had a lot of practice there, guys. So I think if you walk through it individually, pause the video, write down your question and your values, walk through it yourself, and make sure you guys can understand how each combination circuit resolves itself. Okay? Excellent. Well, good luck today, guys. But before I let you go, I want to take care of that question about the costs of running a bulb continuously for 1 year. Now, who runs a bulb continuously for a year? Well, it may not be that uncommon. If you have porch lights that just never get turned off, no one ever sure turns the porch lights off, those porch lights tend to run all the time. And a lot of times, they're the little candelabra bulbs, so they don't take much current whatsoever. But let's look at an example from one of our homework problems that somebody emailed in. Okay, guys, so let's do this real quick. We have the problem, I think it was number 52 from page 547. Calculate the yearly cost of running a 5-watt bulb continuously in an area where the cost of electricity is 10 cents per kilowatt hour. Now, if you guys will remember our definition of power, a watt was a joule per second. And hours is just some different version of time than seconds. So if you had watts, joules per second, and you multiplied by time, let's say seconds, well then the times would cancel out and you would get just joules. And that's right. Actually, DTE charges us for the total energy we use. And it calculates that by a value called power. All right, so let's look at this. I'm going to borrow something from chemistry that I hope you guys will remember. I'm going to say X dollars in a certain power value. 5 watts. So 5 watts. Okay, so what does a watt actually represent? So 1,000 watts is 1 kilowatt. Now this is called dimensional analysis. What I'm trying to do here is introduce a fraction where the top and the bottom are actually the same thing. It's 1 over 1, because 1,000 watts is 1 kilowatt. But by multiplying it by a fraction where it's 1 over 1, you're not actually changing the value at all. You're only changing the units. So right now, watts would cancel with watts. And we have kilowatts on top. So what do we have here? Well, we're missing the time component. The time component was a yearly component. So we're going to need to multiply by the amount of time. 365 days. 365 days. Well, that's 1 year. Now, we're going to convert that to hours by multiplying by 1 day is 24 hours. So days cancels. And what I'm left here with, guys, is kilowatts and hours. And that's exactly what my price is expressed in. The amount of dollars, or cents in this case, per kilowatt hour. So my last step will be to put kilowatt hours on the bottom. For every 1 kilowatt hour, we are charged 10 cents. Now notice, guys, everything cancels. Kilowatts cancels with kilowatts. Hours here cancels with hours here. And the only unit left will be dollars. Okay, so let's just... Okay, guys, the last thing we have here, just multiply under all the numbers. Because remember, even though the units cancel, the numbers don't cancel, just the units cancel. So 5 times 365 times 24 times 0.1. Well, that should give you somewhere around the 4,380. Then, if you divide by the 1,000 on the bottom, the only thing we will get left is $4.38. It only costs $4.38 to run a 5-watt bulb continuously for a year. Ironically, the price of 10 cents per kilowatt hour is right around what we pay in Farmington and Northville. So, pretty crazy, huh? $4.38. That's it. Now, most of our bulbs are not 5-watt bulbs, obviously. You have some bulbs in your home that are 100 watts, or 60 watts, or 120 watts. You have appliances that certainly are going to take more power than that. So, but it'd be interesting to find out by looking at your DTE bill from each month just how much power or how much energy we are using. And of course, we get charged for that. So, if you leave lights on or the appliances on, like the television all the time, you'll find that your DTE bill will be quite large sometimes. Okay, guys, that should wrap it up. Remember to review a little bit today before you take that Google form. That'll be available at 3 o'clock today. All right? On Monday, we'll discuss magnetism for the first time. So we'll look forward to seeing you guys then. Have a great weekend, guys.